some of the chemical properties of organohalides, especially what we're going to use them for. And the main use of organohalides is that they're very useful synthetic precursors. So we can start off with an organohalide and end up with all kinds of different things. Let's take a look at why. Let's take a look at this chlorine. And so remember, this chlorine is more electronegative than this carbon. So we'll have a partial positive on this carbon, which will make this carbon right here very electrophilic. And then also let's think about chlorine itself. If it left here, if it took these electrons and just left, it would be a chloride, which is relatively stable. And so this is overall a very good leaving group. And so if you add some kind of nucleophile, you can substitute out the chlorine for your nucleophile. And so you can see how you can turn these organohalides into all kinds of different things by switching up the nucleophile. And so remember, these are substitution reactions. So we'll learn about two main types of substitution reactions, and then we'll also learn about two main types of elimination reactions. And we'll figure out which one happens when. So again, because this is a good leaving group, we can add a base here, and we'll eliminate out a hydrogen and the chlorine, right, to get an alkene. And so let's just do a quick review of what makes a good leaving group. Remember, a group will only leave if it's stable by itself. And when we're talking about leaving groups, right, they leave and they take the electrons with them, right? So if we're thinking about something leaving and taking the electrons with it, what you can think about is acids and bases. So for example, if we have HI, right, we could draw a reaction where the electrons go on this I, and then we would get H plus and I minus, right? And we know this I minus is very stable because we know HI is a strong acid, and it has a pKa of -11, and that's a very strong acid, which makes this iodine a good leaving group. It's relatively electronegative, and it's very large, so it can easily stabilize this negative charge. Whereas something like HF can perform the same reaction, but not nearly to the same extent, right? I drew this as a straight up arrow. This one has more of an equilibrium arrow because this is a much weaker acid. This pKa is only equal to 3, right? So that's not a very strong acid, and that means that this fluorine isn't very stable by itself. And because it's not very stable by itself, it's not a good leaving group. And so at the end of the day, the main point that we want to get here is we've already learned what a good leaving group is. A good leaving group is a conjugate base of a strong acid, right? The conjugate base of a strong acid. And so we can talk about organohalides, right? Or just, halides in general. Chlorine, fluorine, or chlorine, bromine, and iodine are all conjugate bases of strong acid. Fluorine is not, so it's not as good of a leaving group. But we can talk about other compounds as well. So for example, water versus hydroxide. We can think about which one of these is a good leaving group. So we can think of this as the conjugate base of H3O plus, right? If we think about H3O plus, if it's going to act as an acid, it's going to donate an H plus and leave behind water, in which case this H3O plus is the acid and the water is the conjugate base. And this pKa is equal to -1.7. And so that means that water itself is a good leaving group because it's the conjugate base of a strong acid. Basically, a pKa below 0 is a good rule of thumb. Whereas on this other hand, we can think of hydroxide as the conjugate base of water. Right? If we think about hydroxide and if we think about the reverse of this reaction, right, we'd be adding an H plus to form water, right? So in this case, water is the acid, hydroxide is the conjugate base. And so water has a pKa of 15.7, which is obviously above 5. And so this is overall a bad leaving group. And so you want to be able to identify good and bad leaving groups. It'll become important as we go on. Yep.